C-Therm's purpose is to simplify thermal conductivity testing for the materials of tomorrow. Since 2007, we have emerged as the global leader in test instrumentation. Our core strength in thermal conductivity is built on now industry standard Trident instrument and broadened through strategic partnerships with Rigaku and Metrovid, providing one of the most dynamic portfolios in thermal and mechanical analysis.
Thermal conductivity describes a material's ability to transfer heat energy through conduction. In electronics, whether you're developing a smartphone, aircraft, or electric vehicle battery pack, the thermal conductivity of the materials is a major factor in the overall thermal management of the device. In other applications, like metal hydrides that are used as hydrogen storage media in fuel cells, the thermal conductivity impacts the kinetics of hydrogen adsorption.
The most common mistake we see in industry is applying a good method of measurement on the wrong type of sample. This is what happens when you're limited to a single tool and are facing a variety of sample formats. The Trident was designed to provide researchers with multiple options on a single instrument platform, so you always have the right tool for the job. It's been a huge success. Leaders like NASA, Adidas, Intel, Kimberly-Clark, Lucid Motors, and universities around the world choose C-Therm analysis tools and the support we provide.
C-Therm customers get access to the most advanced transient methods and are able to test under real-world application conditions, including humidity, temperature, or pressure. C-Therm's patented MTPS single-sided sensor is the fastest and easiest way to measure thermal conductivity. The Flex TPS is brilliant for more challenging applications and testing anisotropic and thin film samples. Our needle probe offers robustness for polymer melts. And the new THW is great for low viscosity fluids like engine coolants.
Not every client's ready to bring testing in-house, so we also offer industry-leading testing services here at Thermal Analysis Labs. C-Therm's highly skilled and experienced team provides access to the most advanced characterization tools for thermal properties and the expertise to make sense of the test results. For example, Rigaku's breakthrough sample observation capabilities allow users to video record a sample as it undergoes a heating cycle. When working with an unfamiliar material, you can see phase changes, crystallization, and other phenomena. This is vital for understanding the material and helping tell the story of how it behaves.
Metrovib's line of DMA offers the broadest frequency range and the highest force available on the market. This is just one of the reasons it is the standard in the rubber and tire industry. We work with a lot of folk developing different fillers for tires, including carbon black. And due to its sensitivity, the DMA is by far the best method to measure the glass transition point.
C-Therm aims to help accelerate material research and improve outcomes driven by better material performance data. Let us help you get the best possible data for your research. Simplifying thermal conductivity.
Alrighty, good day, folks. For those of you who are in the lobby or sorry, in the session right now, that was just a little preview, a little background video about C-Therm. We'll get started with the official session here in about a minute or so. Just give some folks some time to join today's session. Just a few housekeeping items for those of you that are here right now. As we're going through today's presentation, if you do have any questions, either related to the content presented or anything maybe relevant to the work that you are doing, please feel free to make use of the Q&A feature. So there's a Q&A button at the bottom of the screen there. Near the end of today's session, we'll have some time to answer those. So if there's any burning questions that you have, please feel free to do so. And the last little note, as I'm going through, if there's any content that I'm presenting or referencing specific links or resources, my colleague Emma, who is on the call here today as well, she'll be posting some into the session as well. So if you're looking for those links, they'll pop up for you. Of course, all of this will be all available on our website as well. Today's session is being recorded, so if for whatever reason you have to drop off early and you want to check what was talked about in the later half, or if you have a colleague that maybe wasn't able to make it here today, and you want to share this with them, there will be a link available for the playback of today's session. All right, I think that's most of the housekeeping stuff. So with that being said, let's go ahead and jump right into it. So welcome everyone to our first webinar of 2025. Thank you for joining us here today. My name is Arya Hakimian. I'm an application scientist here at C-Therm Technologies. And today we're going to be going over really how to quantify textile performance, looking at measuring the warm feel, cool touch of fabrics. So that'll be the focus of today's session. Going to do a little bit of a just general introduction here. So C-Therm, if you're unfamiliar, we are a group that focuses on thermal conductivity, thermal effusivity characterization, specifically leading transient methodologies. We have a global network of distributors with customers all around the world. We work in various industries. Today is obviously focused on textiles, but if you have other interests for thermal characterization, whether that be everything from EV batteries to baby diapers, we've run into it. So, but again, today's session will be focused primarily on textile characterization. I wanted to introduce the platform that's going to be the basis for really the methods that are used for today's session. So Trident, you can see here, Trident was launched, I believe, in 2019, and it is a multi-method system available for a variety of material characterization, really depending on the sample type that you're working with, the application conditions, the sample format or size you have available. One or more of these methods may be more appropriate. Specifically in today's session, we'll be focusing quite heavily on the MTPS method, and a little bit on the flex transient plane source, or TPS, sometimes referred to as the hot disk style sensor, to a lesser degree. But these will be the two that we'll look at here today. Just for those on the line, if you're interested or curious what the other ones are for, this one here, again, won't be talking about it in today's session, but this is a transient line source. It's a needle probe style sensor. If you were doing work in the field of, let's say, polymer melts, injection molding, if you're dealing with maybe more chemically aggressive like fluids, or in geology, there are some applications where this could come into play. And the hot wire here, this is predominantly for liquids. If you're doing engine coolants, immersive cooling technologies, things of that sort, that's where they would come up. But again, not a focus for us specifically here today. And Trident really being a multi-method system, it was developed with really this idea in mind. And this quote is one that we like to use a lot. But when all you have is a hammer, everything looks like a nail. So the idea with this and the reason it relates is when we're looking at broader industries for thermal characterization, there are certainly some times where one method is better than the other. There's times where maybe more than one method could be used. But if you're locked in with just one option, you're going to try to make your testing fit around it when it might not really be designed for it. So really this is the whole purpose of Trident. It gives you that flexibility to pick and choose the best tool for the task at hand. Now, if you're new to thermal conductivity, thermal effusivity, thermal characterization in general, we do have a method selection guide available as a free resource. This is a nice piece that you can, get yourself up to speed on certainly the methods that are available on Trident, as well as some of the other methods that are available in industry. So if you're looking to maybe learn a little bit more, this would be a good starting point. I'll also mention, so see, I kind of said at the top of the call here today that we focus on thermal conductivity, thermal effusivity related properties, but we are partnered with both Rigaku in North America as well as Metrovib for their line of thermal analysis, DSC, STA, TMA, and then Metrovib's DMA systems. So again, if you did have other characterization needs that you're looking to bring in-house, we can certainly support those discussions as well. And I will mention Thermal Analysis Labs, TAL. So this is C-Therm's contract testing division. If maybe you're looking to get some materials tested, but you're not really at the stage or at the volume where you're looking to bring something in-house to do it yourself, we have testing services for all of our methods, again, as well as other methods that are available in industry. So certainly happy to have those conversations if interested. Before we go into it, I always like to, really find a testimonial, maybe speaks to the application space. I really like this one. It's short and to the point. It's from Dr. Christian Hyde he's a sport science manager at Adidas. And his testimonial, his quote to us was, "The device is working perfectly." So couldn't really ask for anything better than that. We do have a range of other testimonials on our website. Might give you a flavor for the types of groups that we're working with. Again, it's quite a wide-ranging field, or wide-ranging fields of application, but certainly check that out on our website if you're interested. All right, so thanks for bearing with me for that kind of introduction there. Now we're going to really go into the bulk of today's session. So we're doing really, again, a look at textile performance. A lot of what we'll be focusing on today in textiles is really around that warm feel, cool touch aspect, something that's quite broadly been adopted in the field of apparel, sports goods, any type of application or product where it's going to be worn or in contact with the human body. This type of characterization is quite relevant. There's a few academic publications that I'm going to highlight near the end, which have a little bit more of a spin on them in terms of some of the, I'd say, more novel use cases. But we'll go into, take you through the basics and then get into some of those more unique use cases as we go through here today. So again, I want to just start out with, really the basics here. So thermal conductivity and effusivity. So let's talk about those. What is thermal conductivity? Well, effectively here, this is a measure of a material's ability to conduct heat or transfer that heat energy. This is an intrinsic material property, so it's independent of the size or the shape of the material. There are certain properties which are, perhaps dictated based on the thickness, like R value. If you're doing work in insulation, that might be something you've heard of. So R value has, for example, thickness component mixed in with the thermal conductivity to get there. So obviously, if you change the thickness, you'll change your R value. Thermal conductivity, on the other hand, is independent. Now, of course, if you're densifying the material or changing some other thermophysical properties, that can play a role. But if you took a material of A that was 2 millimeters thick, and then you took that same material but it was 10 millimeters thick, it will have the same inherent thermal conductivity. Now, what is thermal effusivity? And again, this would be a little more relevant to the bulk of today's session. So thermal effusivity, it's sometimes referred to as thermal inertia, but really this defines a material's ability to exchange heat with another body that it's in contact with. There's some neat calculations you can run on the interfacial surface temperature upon contact between two different bodies of different, different temperatures, different values. But they're related here, right? So this is, your units for thermal conductivity, watts per meter Kelvin. But thermal effusivity, you can see it's equal to the square root of K. So thermal conductivity, density, and heat capacity. So these are related thermal properties. But again, it's really the guise of which application space that you're in, and one might be a little more relevant to talk about than the other. But so when, thermal effusivity is somewhat newer for some folks, I find. So this is a neat little thought experiment that we do with some folks to really just help illustrate the point and what it is. So I'll use this example here. We have a desk, right? Let's say this is real wood. I'm assuming it's a composite, but let's say this is real wood, and then there's the metal bars on the side. Which one do you expect? Which one would you say is colder, right? If you went to touch, let's say, put your hand on the wood, and just from that perceived feel, and then right after that, you're maybe to go to touch the metal. I would say what you're likely to find is that the metal is going to feel cooler. But technically speaking, this desk just in a room, assuming there's no heat source connected or cooling system like directly on the part, they're technically at the same temperature. So the temperature is the same, but the perceived feel is different. And again, we can relate that to effusivity. And that's kind of the core idea behind what we're doing here in quantifying performance of things like textiles that are, again, in contact with the human skin. So textile 1 versus textile 2 having different thermal properties can give different sensations or perceived feels, which can, again, be correlated to comfort. So this here is I'll call it a very general example breakdown of we call it the warm feel, cool touch product performance index. So warmer feeling materials will typically or will have a lower effusivity. As you can see, the closer we get to 0, the more warmer feeling that is, whereas the opposite is true for the more cool feeling samples. Higher effusivity, more cool. Now, when we look here, we can see some very specific, like, sheep's wool, 94, linen, 201. These are generic examples because one of the things to really keep in mind is the material plays a specific role here, and the material characterization is one aspect, but especially in textiles, there's a lot of factors that go into this. Let's say you had 10 cottons, but you have different yarn sizes, different patterns of construction. Maybe some have treatments done to them. These can all impact really, the effective range of where those are falling. And that's something to keep in mind because as you're developing, look at like a t-shirt or a shirt here, if you're looking to maybe gear this product to be more of a fall winter product line, well, you're probably going to want to push your values here to the left, find materials and constructions that yield lower effusivities because it will give you more of that warmer feeling. I got this nice thick cardigan on because that's part of what I'm trying to keep warm here in the eastern part of Canada in January. Whereas in the summer months, of course, or if you're an athlete and going to the gym and you're, going to be, exerting yourself, you want to stay cool. Maybe using some of these more higher effusivity materials can be beneficial. So that's kind of the idea of where this is all playing out in terms of why are these properties relevant and where do they come into play in research and, of course, in industry as well. So effusivity, amongst other things, can also be really useful in claims validation. You'll see different things, mattresses, footwear, shoes and apparel, shirts. If there's notes that say, feel cool to the touch, keep feet cool, cool all night, things like this can actually be backed up with the measurement of thermal effusivity. There are some groups that we work with that I know internally they have a certain threshold for which they require their vendors' materials to hit in terms of an effusivity value to be brought into specific products, product lines. So, you know, whether it's for material sourcing, like marketing claim validation, internal R&D, this can be quite relevant and very useful depending on the you know, the scenario or the case that you're looking at. This one here, this is just kind of maybe a little example of that, you know, backing up some claims. There was a group a while back, Arctic, they had this cooling, it was actually a PCM cooling technology that they were applying to materials, and it was applying a more cooling sensation when in contact with the body. This was very valuable to them, especially if you were able to get out in front of a client or a prospect, you know, bring them some, you know, examples, one that's coated or one that's treated and ones that's not treated, and they could feel the difference. You know, obviously it's really easy to sell that. But, you know, a couple things that can be subjective. You know, there's some amount of cooler feeling. How much, if I use your, you know, product A that does this amount of cooling or this, like how much is the difference really? And also, are you able to get in front of your client, especially with everything recently? I mean, everyone knows past years going quite virtual. Sometimes it's not as accessible to, you know, go directly to someone physically. You're doing a lot of online meetings, and, you know, how can we show that? So this was basically one of the reasons we did some testing here. So this is just a very small data set just to illustrate the point, but you can see there was both, this is noted to be an interlock fabric. The other one was a non-woven high loft material, both treated on the left and then untreated on the right. And what we're able to show here is, one, you know, visually show, you know, there is a notable difference here, but also really quantify by how much. So again, what was, you know, previously subjective or required you to, you know, get in front of someone physically, you can now back up some of these claims through actual material testing to help really solidify your point. So yeah, this is just one example here. This was some testing done on the MTPS, and we'll go into that method here, actually, I believe up next. So of the methods that were available on Trident, I mentioned MTPS will be a big one for us here today. So MTPS stands for Modified Transient Plane Source. This one is C-Therm's proprietary sensor design, and again, one of the 4 available on the Trident system. You know, you can see a picture of it here. It's, you know, at a very high level, the things that I'll flag, the active area of the sensor is this colored region right here. It spans about, spans about 18 millimeters in diameter. So when you're looking at your sample size requirements, really the big one, there's a few other considerations, but a big one is that we can at least cover the surface of the sensor. You know, so it doesn't have to be circular in nature. It can be a square. It can be much wider. You don't need to cut it to size, but we do need to make sure we are making contact and covering that active zone. That'll be really, I'd say, step number 1 to be able to use this method and get valid, reliable, and repeatable data. So for the purpose of today's session, I won't go super into the weeds here, but just for those that may be interested in like what's actually going on in the measurement, essentially here, the sensor, there's a spiral heating element embedded on the top side of that sensor face. This is what's delivering a thermal input to the system for measurement. So your sample, of course, is placed over top here. And then what we are doing is monitoring the change in temperature that occurs as a function of time. Different materials, you know, something foam, like more insulative in nature versus something metal, more conductive. And again, you could interchange conductivity, effusivity in some cases here, but they will respond differently to that introduction of that temperature gradient. but it's based on the rate of change that is observed during the measurement. This is what's used to determine the thermal properties of your material. And the nice thing about the MTPS in particular is that all of the settings for your measurement and all of the data analysis that happens post-test is all handled automatically by the software based on the calibration that you select. So there, again, the MTPS is employed in a variety of fields from, conductive metals to polymers, liquids, what have you. But specifically to textiles, there are some textile-specific calibrations that are available. And when we talk about the ASTM standard, which might be the next slide or a few slides down, those are the ones that you would use to conform specifically to that standard. Yeah, like I almost made the slide deck myself. I knew it was up next. So ASTM D7984. This is the standard, I'll read it out, standard test method for measurement of thermal effusivity of fabrics using a modified transient plane source MTPS instrument. So, a couple things to note here. The MTPS, again, being a proprietary sensor design, to conform to this standard, there are certain requirements, part of, the MTPS method inherently. So if you are looking to do testing according to this standard for thermal effusivity, it is done with the MTPS. There are also some, additional, of course, like guidelines and requirements to conform to the specifics of the standard, things like temperature requirements, humidity, the conditioning of the samples, etc. But overall, what is involved in your setup for this? You, of course, have your MTPS kind of shown in this diagram here, your sample over top. This is a kind of a graphic representing a CTA or compression test accessory, something we'll talk about here, the influence of compression and where that can play a role in characterization. This is then connected to the controller unit, so that'd be your Trident, and then connected to your laptop or computer. So pretty straightforward setup there. Yeah, the overarching message would be, if you're looking to have ASTM D7984 specifically, it would be something to look, especially if you're looking for a group perhaps to do this testing for you, just make sure that they do have access to the MTPS method. Now, that being said, I do want to talk about one of the other methods here, which is the more traditional transient plane source, or TPS. And traditionally, in years past, the TPS wasn't really the method we would talk about, especially for effusivity. Still for textiles, a little, not so much, but for effusivity. But there's been some developments within the ISO that I do want to bring up. It's something that different groups that offer TPS, as well as ourselves, have began offering. But there are certain considerations I just want to flag around this method in general. Not going to go deep into the background behind this one. Just wanted to really flag some verbiage in the ISO standard. So when we're looking at thermal effusivity, ISO 22007. The -2 variant is the TPS usage for testing like thermal conductivity and diffusivity of a variety of materials, polymers, foams, metals, etc. But the -7 variant, this came out at the end of 2023. So, about a year now it's been out there, as a way of getting effusivity from your TPS. Now, the way this is done, it is, the TPS provides you conductivity and diffusivity with some other things. You can get it provides a calculated effusivity here. But a few notes. The error on the measurement is a little bit higher than that of the MTPS for the effusivity measurement. 10% here versus about 5% on MTPS. And there is some work that can be done in TPS in a single-sided operation mode. By default, it's a double-sided method. So you usually place a sample on the top and bottom side. You create a stack. Again, it's a little bit different than the MTPS requirements. But there's some, general verbiage here on, ideally you're going to use the double-sided method because that's what gives you your best possible output. But for a lot of the effusivity side of things, there's discussion around the single-sided setup. Again, it's something that can be done, but just understanding some of the differences and limitations there, I think it's important for folks to know about. And the big one here is it does not conform to the ASTM standard. So, just as a keep that in mind. Depending on what you're looking to get out of your measurement, if it's more for internal R&D, for product validation, or if you're looking to conform to a specific standard, these different things can play a role in which method is really going to be the best fit for you at that given time. So moving forward here, some recent thermal effusivity collaborations. So I just wanted to bring your attention to, if you've been on some of the webinars over the past year or two, you might have already seen these. And I'm not going to do a full rehashing, but I did just want to kind of put them out there, give you a link to where you can look them up if it's of interest. It's some nice work that we've done in collaboration with a couple different academic institutions. So first one here is the work that we did in collaboration with the University of Oregon, looking at the perception correlation to thermal effusivity. So remember back a few slides, I showed you that warm feel, cool touch index, and there was kind of like warm over here and cool over here. Again, where this is a subjective experience, the effusivity provides some guidelines, but really matching and lining that up with what, a human test panel would describe as warm or feel was something that we wanted to really kind of go into and investigate. And that was the essence behind this study. So what we're showing here, it actually lines up quite well with the kind of just the older graph that we had, but you can see that generally speaking, part of this, I won't go into the full study, but they got participants to touch different materials across different ranges and basically start to like arrange them where they felt one was warmer or cooler feeling. So you could generally show that anything, definitely below 100, but up to anywhere from about 122.8 on the effusivity to about 169 was considered by many warm feeling. Of course, there's this little gradient in the middle where there's some overlap, but generally speaking, above 162.5 and higher was cool feeling. We did the analysis on both the face and back sides of fabrics because sometimes there can be differences there. And if you're in an apparel group, that might be important because if you're looking to, let's say, tailor the sensation of the inside of the material that's in contact with the skin, that could be a very important consideration. But I don't know if most folks do this, but if you go into a store and you're looking at clothes, first thing you might do is like grab it and feel it. So you're touching the outside. So those, if you have different performance outputs of those two different sides of a sample, sometimes that can really play a role in the psychology and the perception of, even quality. So something just to keep in mind. But generally speaking, as a golden rule, I would say, really if you want to describe your material or, claim your materials to be cool feeling, you're definitely going to want to be on the closer upper end here. I know there are some groups internally that, they basically set a benchmark or a threshold, and, if you're above this, you're in. If you're below that, you're out. So always good, of course, to have those discussions with the relevant parties. But, this was something that if you were interested in learning more about, again, there was a panel discussion as well as a specific rundown of a webinar on this topic with the researcher at the University of Oregon, Susan Sokolowski, and there was a publication there in a conference proceedings for some of the data as well. The other one, and this one's a little bit more recent, C-Therm's collaboration with the University of Alberta, looking at dry versus saturated textile testing. So in the ASTM standard, it's all benchmarked around the effusivity of the material, but really in under relative humidities, but dry, like they're not saturated by any means. There's been some work, and there's actually some kind of older data I'll show, which kind of goes over how the impact of a semi-saturated or fully saturated material can play into the effective thermal effusivity output. But this was some efforts in really trying to codify more of some guidelines around this, working to develop an SOP for specifically wetted applications. Again, some nice work that came out of this, again, available for review on the recording on the website from last year. And again, I believe there's being some content published on this as well. All right, going into some just varying application examples here. Just want to kind of do some quick hits on, stuff that might be relevant or, things that we come across quite a bit and wanted to, pass that knowledge along. First one here is understanding the influence of compression. Especially important is if you're dealing with a very lofty material. If you're applying a force, squishing something down, what's happening here? Well, your sample thickness goes down. And I mentioned earlier these like the intrinsic property, but this is different because in these scenarios, it's not just a thinner sample, it's thinner, but you're actually changing the density of the material. This has an impact on the thermal resistance and, conversely, the thermal conductivity and effusivity. What's really happening here is if we look at a system, you kind of zoom right in, it's, you see this fluffy solid, but inside of that is a lot of air. Air is a very strong insulator. It has a very low effusivity, very low conductivity value. So the more air that's present in a system, the lower it will be on that side of things. Compress that down. Well, what are we doing? We're putting the material in closer contact with each other, pushing that air out, and again, tweaking and changing that effective performance of the material. I really, again, kind of an example to like you could think about in this case is, excuse me, if you had, let's say, a winter jacket, like the really puffy ones, the big puffy winter jackets. Well, that's filled with some materials, maybe similar to this. But when you kind of see the jacket, it's just, it's contained within the envelope, I'll say, of the material of the jacket, but it's quite lofted. It's not it's not like pushed and squished down all the way. And because of that, again, it keeps you warm. It's more keeping some of that heat in. But the flip side to that is that same material could maybe also be used in a sleeping bag, right? So, that same fluffy stuff in a sleeping bag, but when you are lying on a sleeping bag, it's definitely not super light and fluffy. You're compressing it down. So if you are developing a winter jacket, you may want to have your materials under a specific compression condition versus if you're doing the same material development, but for something in use of, let's say, a sleeping bag, you would want to change those parameters to, again, get at the more representative output of those results to really, again, understand the true performance of the material under those different conditions. Yeah, here, just quick example. This was a kind of a similar lofted sample under different applied force loads. And again, generally rule of thumb, you apply more force, you're compressing it down more. That's going to bump up those effective values of the material. This one here, this is a publication from a while back. Well, I say 2017, and a while ago now. It's not on textiles, but it's on a bio-based insulation. It's a building material application, a little bit, again, kind of, left of center here for today's discussion. But I wanted to flag it because it's a really nice data set that they produced in this study, specifically just looking at the one on the right here, because what they were doing, and this would have relevancy to textile characterization in general, but they were cycling the relative humidity of the environment that the material was placed, and doing this, it was quite a long term, it was about a month-long trial to assess the performance of these materials and to see how much of a drop or increase occurred under different relative humidities. And we can kind of see this, this wavy trend, pretty consistent there. But it's interesting to note because, under a higher relative humidity, again, absorbing more of that moisture. This one here, I'm not going to read the code. The one in green, you can see at a high relative humidity, this was based on conductivity here, had the highest value. But when we drop it down to a lower, it actually has an even lower one than, let's say, the black one or the blue one here. So it used to be the highest conductivity material under X condition, but it was kind of lower end under the lower one. So understanding which materials you're going to select is also very important to see how they respond to these different environmental conditions. Again, it all comes back to that representative testing capability and why it's so important to understand my material is this, but I'm going to be using it under these conditions. So how do I best benchmark the performance to make sure I'm really getting that apples to apples comparison of how it's going to be used in application? This one here too, this one is on so performance characterization of diapers. How does the thermal effusivity provide insight into this performance? And again, it's coming up for the third time, the representative testing conditions here. So, I'm not going to do a full breakdown of the diaper side of things, but generally speaking, you've got three parts. There's an absorbent core, a surge layer, and a top sheet. Now, what you may be interested in is, well, how do different diapers perform against each other? And, what would that overall sensation be? Parents out there, if you've got a baby and they're crying, you probably do anything to make that stop, right? So providing you ways to make them more comfortable might be a really great option here. So the example that we're showing is testing a no-name brand versus one of the leading brands. We started with dry testing, so just kind of the dry material popped on top of the sensor, and they were quite comparable, really. I call this a fairly negligible difference. But when you go into that wetted state, now this is pre-development of the SOP that we worked on with the University of Alberta. This might have been a little more crude, just applying saturating the sample and then popping it on the sensor immediately for testing. But in either case, it was kept the same for both samples, and we showed that upon initial wetting and then testing, that no-name brand kept things feeling much cooler. So you could imagine, I'm assuming part of that three-component structure of the diaper, it wasn't pulling that liquid away to that absorbent core as fast, so it made a more cooler feeling sensation because water will really pump up that effusivity value. But in this scenario, being cold in that sense is less desirable. You want to, pull that away to get them back to feeling more of about as close as you can get to that dry state, right? So upon initial wetting, we do see that the no-name brand was significantly lower performing compared to that leading brand, even though they both started out very similar. And then looking, 12 hours later, we do see, of course, it doesn't go quite back to baseline, but because there's still some partial saturation, but again, much more comparable than the initial wetting. But again, you'd say, is it worth paying the extra money for the leading brand versus the no-name brand? Well, maybe sometimes it is, sometimes it isn't, but just a quick data set illustrating where that might play a role. All right, getting towards the end here, I did want to just finish up with a couple textiles publications that were from last year. So these were just kind of was looking through, just picked a couple that were interesting using MTPS, and they had a focus on textiles. As I mentioned, these were a little more novel use cases, and we'll go into that a little bit here. But just wanted to kind of share this with you guys, some interesting data out there. This first one here is published in Nature Scientific Reports. The title here, Facet-Dependent Ultra-Low Thermal Conductivity of Zinc Oxide-Coated Silver Fabric for Thermoelectric Devices. So it's an interesting one because we do a lot of work in electronic devices, batteries, thermal management. But this one, it kind of takes that side of things and brings in a fabric and kind of melds those two worlds together. So it's an interesting one, wanted to share it. I won't do the full breakdown here, but basically they were doing various concentrations of our two starting materials and introducing that onto a silver fabric. Through the process here, you can see, we get to the end, and you have a zinc-coated silver fabric, essentially. But depending on the ratio of the starting products here, this would infer some differences in the type of zinc oxide that was produced on the fabric, and they were looking to see if that played a role in the overall thermal performance of those coated systems. And it turns out it did. So again, they provided thermal effusivity and conductivity as the main output here from their results. And I'll just say the targeted goal for this was to actually have the lowest value possible. So interestingly, when they started with just their pure fabric here, I'll just use this line as the example. We, sitting a little bit above 55 milliwatts or so, right? Through the introduction and when they were forming Oh, that's the type. That should be Z2. Sorry. So the Z1 and Z2 formed a crystal structure in the 101 direction, and they were higher. They ended up boosting that performance compared to the Z3, which was the 100 direction. And as we can see, these two actually went the opposite route that they were looking for. But then the third variant there did actually show a performance, I'll say, increase, because the conductivity and effusivity decreased for this specific application. Interesting work. It's a textile, it's a fabric, not something I think that's being used in necessarily a gym shirt or a pair of shorts, but it's textiles. Interesting work here at the MTPS, looking at that performance of those different material treatments. The next one here, titled Through Thickness Thermal Conductivity Characterization of Dry Carbon Fiber Fabrics. So again, this was a recent publication from last year using the MTPS. Again, this one was really purely focused around the conductivity side of things, but they're looking at these types of carbon fibers in their materials. So in the paper here, you can see a nice little picture of the setup that was used. This is, again, that CTA, compression test accessory. We have the MTPS below it here, and then the different carbon fibers that they were looking to assess the performance of. When we look at the data set, they actually did some interesting things here. I believe they had it set up in a vacuum chamber, but they were doing testing of the materials under ambient and then under vacuum conditions. As we can see, that's a quite notable difference in the effective thermal conductivity. So interestingly, these types of conditions can be as simple as just adding a little water, or putting it in a vacuum, or under different atmospheric conditions. I will mention that the MTPS, the TPS, and TLS methods, they do have options available for some of that more novel testing, doing things under different controlled gas pressures, inert gases, under vacuum, etc. So again, maybe you are doing some more exotic, novel material testing, and if thermal conductivity is playing a role there, love to have a discussion with you, see if we can support you in any way. It's definitely something that we have a history with, and as you can see just from the numbers here, it can sometimes have quite a big impact on the performance of your system. Well, that really almost brings me to the end of what I was hoping to get through here today. I've got a few little outro slides here just to close things off, talk about some upcoming events and webinars. Again, if you do want to stick around for that Q&A, please feel free to do so. We'll go into that here in a few minutes. Also, I've noticed a couple questions that have come in already. If you have any questions, type them in. I'm going to go top to bottom, and we'll try to get through as many of them as we can. So additional resources, if you're looking to, just, get some more information, our website is full of, like I said, past webinars. We have a tech library, so you can search for different databases, search through our database for different publications that we are featured in. So if you're looking for some content, definitely feel free to give that a look. I will put a little plug in for our upcoming webinars. So we've got one on the books here for the end of the month. This one is going to be a very different application focus, but the role of thermal conductivity in solid state hydrogen storage. Excuse me. So this is actually a picture of the one of our hydrogen gas cells that you can integrate specifically here with the TPS method. So that's really going to be featured here. We have guest speaker Dr. Jacques Huot from the University of UQTR in Quebec, Canada. And as far as in-person events, where we're going to be traveling for some shows and conferences. So again, end of the month here, we'll be at Nanotech 2025, which is in Tokyo, Japan. We do have a booth set up there. If you're in the area, definitely feel free to stop by. Love to have a chat. We will then later in February here be at the Thermal Management for EV and HEVs. This is being held in Munich in Germany. Again, that is coming up, the 25th to the 28th of February. And then lastly, PickCon. This is going to be more for I'd say the North American market. We're going to be in Boston, USA. That is scheduled for the beginning of March, so March 1st to 5th. So if you're in the area for any of these and you're interested in kind of what we're doing, it might be relevant to your work, certainly feel free to swing by and have a chat with us. If you're not going to be in the area though, but you still want to learn a little bit more, and again, maybe go a little deeper specifically on your applications and your materials, we welcome you to reach out to us. We can set up a technical consultation. It might be with myself or one of my other colleagues to go through really your application needs, your testing requirements. We can kind of set up some demonstrations to show you what it all looks like in practice. And kind of go over some of the more technical details in further detail. Or maybe you're just looking for some budgetary information. Certainly feel free to request a quote. Happy to provide that to you as well. Last little shout out here, if you want to keep up to date really with everything that we're doing, give us a follow on LinkedIn. That's going to be really where we post all the latest and greatest content, upcoming events, different application highlight, write-ups, things of that sort. So yeah, give us a follow on LinkedIn if you haven't already done so. And with that brings me to the end here. I'd just like to thank everyone for your attendance and joining us here today for our first webinar of 2025. Again, we're going to go into the formal Q&A session at this point. If you are dropping off, though, and maybe you still want to get in touch, info@ctherm.com. Definitely a great way to reach out to us. Someone from the team will be in contact. So for those of you that are dropping off, once again, thank you for joining. This will conclude the end of the formally recorded session. Again, for those that want to stick around for the Q&A, bear with me for a minute, and then we'll go into that.